customize that for you.
Talk louder, that way you can go through the mic.
Oh, you can hear me back there, right?
Okay.
I used to be a singer.
Oh, there you go.
Yeah, I know how to project. Anyway, Pavel's going to give a great presentation, so we give you your attention here.
I hope it's great.
Phenomenal. So anyway, take it.
All right, I'm going to discuss a little bit what your car is under its skin. Primarily, I'm going to focus on the structural aspects, the high-strength steel, the crumple zones, and I'm going to go into high voltage systems. I'll go through the main components of it, and then the HVIL through the car. And then after that, I'll go a little bit into the architecture of the battery pack, the BMS, and Ian's going to talk about the battery brick that he brought over. And then, since everybody's super curious about our last project that we did was the trolley bus, I'll go into a little bit of detail on that. I'll go into the drive axle system on it, the controller, and the battery mods that we had to do to make the thing work. So the first thing, this is a cutout basically of a shell, of a Model S shell. On the shell, it has the front reinforcement. It's not on there right now, and that kind of holds the front together. It's made out of a high-strength steel, very heavy. And then in the back of the car, you got a rear reinforcement made out of steel as well. And what that does, when you get rear-ended or you crash into something in the front, it'll keep the front more or less together. And then with cars with third row seats, it has an additional aluminum cross member that gives it even farther strength so it doesn't hurt the rear seat occupants. And then this highlighted stuff right here, that's made out of high strength steel as well. And it's a little bit tricky since the whole body is aluminum. You can't weld the steel portion in it, so it's mostly glued and riveted. And what this thing does, sorry. Okay, is that better now? All right, sorry. Anyways, what this thing does, if you flip the car over in the event of an accident, it'll give it a lot of strength because it's mounted through the whole car. And then on the bottom portion of it, we have a bunch of aluminum beams, which gives it the torsion, like in case you're impacted, it'll prevent the battery getting damaged and potentially starting on fire. There's not a crumple zone in this area because you don't have much space between the outside of the car and your seat. Now in the front, part of the reasons why a Model S and Model X and any Tesla and most EV vehicles are so safe, they don't have an engine. It's all hollow. So how it's designed in the event of an accident, that big beam in this area, it will, did I lose my sound or no? Am I good? No. All right, I thought I lost my sound. Anyways, what this will do is it'll crumple in the event of an accident. How the whole thing is set up, it'll actually crumple so it goes in a certain direction so it doesn't penetrate like inside the cabin or towards the battery pack. Over here you can see the little like a dent, so in the event of an accident it'll bend in this area. This car that this is a picture of, it's one of the cars that we were repairing. It hit a deer. You could see there's absolutely no structural damage, but it did take out this upper rail. And in order to fix it, you can't straighten it. You have to replace the whole upper rail in a Tesla. And it's just welded and glued on. Now I'm going to go into the components of a Model S, which make it power. This first component, it's located underneath the rear seat, and it's called the high voltage junction box. And what basically this thing does, it's like the fuse box in your house. All the high voltage connections go into it and then distributes everything where it needs to be. And it's basically what makes the front motor power, what makes the rear motor power, what makes the battery heater go, the DC-DC converter, everything. Next component is the charger. The charger is also located underneath the back seat. This is a first-gen charger. Second-gen charger looks a little bit different, but it's located underneath the back seat on next to the junction box. And if you opted for a dual charger car, the slave charger will be located on the driver's side. So the master is located on the passenger and the slave is located on the driver's side. And essentially what the charger does, controls the charging. It converts AC voltage that you get from the outlet into DC voltage, which the whole car is. It also has a capacitor in there which will up the voltage pretty close to the battery's 400 volt operating system. Next we got the DC-DC converter. This is the older style DC-DC converter, and essentially what this thing does, it basically takes 400 volts and then converts it to 12 volts to power up the 12 volt battery, which powers all your electronics inside the car. It also has some outputs for the climate control. That still gets controlled by 400 volts, your heater. And there's the battery heater that controls it. And the AC compressor, I believe this is the AC compressor. And this also has coolant going through there. This is the first generation DC-DC converter. They kind of put it in a bad spot. It's located right behind the front passenger wheel. So if your inner fender got damaged or something, all the dirt will fly directly into it. In the later cars, they put it in like in the center of a car in the front, so it's in a much safer place, and I hadn't seen any of them fail yet. Next is the drive unit and the inverter. So the drive motor, electric motor on here, it's right there, and this part of it is the inverter. And basically what the inverter does, it takes the DC voltage from the battery and then converts it back to AC voltage to run the main motor. And in the Tesla car, there's no transmission, so this goes straight into the differential. The performance cars, they have a little bit stronger inverter for the extra power that they can produce. This is a large drive unit. It's found in the rear-wheel drive cars and the performance cars. The small drive unit is quite a bit smaller, and it's identical in all-wheel drive, on non-performance all-wheel drive cars as the front and the back. They're the same, they just have a little bit of different gear ratio on them. Now we got the main battery pack. This is a picture of a 85 kilowatt battery pack. Yes, basically an all-wheel drive car, your main motor is the rear motor, and then the front motor is the slave motor. And essentially the rear motor sends the signal to the front motor and tells it how much power to produce, how much power to take, and that's how they run them. It's basically it's an open differential in them, so it's just like a normal car going through a differential. And the front motor is a different gear ratio than the rear one, so I think the front one is geared taller and the rear motor is geared more short. So like off the line, you're mostly getting power from your rear motor, and then when the speed gets up, the front starts to pull more, which is really smart how they did it, because like if you launch the car hard, the weight comes off the front wheels, and you don't want them spinning, so that helps to have the taller gear ratio on it. Sorry. All right, back to the pack over here. This is an 85 pack, and how I could tell it's an 85 pack, it has the 2 extra battery modules in the front. 70 pack or a 75 pack and a 60 pack just has those modules and does not have those 2 modules in the front. In the back over here, that's where the BMS lives, the battery management component. You could see the 2 little red things over there. Those are the contactors, and they're like the on-off switch for the high voltage system. And then the main safety component in the Tesla, I'd say, is the high voltage interlock loop. One easy way to disable your car, I don't know if you guys noticed, if you open your front, it says like the first responder loop, and it has like the little cutters on there. So basically what that does, if you cut that, that opens up that whole loop. And essentially how the loop works, every high voltage component, so the motor, the charger, the DC-DC converter, they all have HVIL in it. And if it's something that's unplugged, it breaks the loop and your car will not work. The HVIL is controlled by the 12 volt battery, So eventually, if your contactors are open and there's no 12 volt, your car stays disabled as well. This is a layout how the battery pack is laid out. So I don't know, it's hard to see probably from back there. Essentially, it's all in series. And this is module 1, module 2, module 3, module 4, and then they kind of interconnect. And then we got the negative starting here and the positive ending here. And the voltage is going to be the highest right at the contactors. So if you have to take a Tesla battery pack apart, make sure you don't touch two things at once, because if you touch the negative and the positive at the very end of the battery, you're gonna have around 400 volts going through you, which is not a good thing. So when you're working on a battery pack, use one hand. Since the battery pack is totally isolated, you can either touch the negative or the positive. As long as you're touching it with one hand, you will not get electrocuted, because it's a sealed system. Yes, 80 of the 70s are around 350 volts, and then 85s are around 400. What they're rated for. Oops, I'm going the wrong way. And then I'm going to go a little bit into the battery management systems. Like I said earlier, the contactors, that they're like kind of the on switch for your high voltage system in the car, and you can hear them work. Like every time you open the door when the car is asleep, you'll go click, click. That means the contactors are closing and powering up the high voltage system. And they do it roughly about every hour, because each time, every little hour or so, the gateway, that's the main computer, it does the system check, and it wants to make sure that the 12-volt battery is in good health. And in order, on the older cars, in order for them to charge up the 12-volt system, it has to close the contactors and send the voltage through the DC-DC converter. And contactors are also a huge safety feature. In events of an accident, basically the HVIL loop will break and it'll open up the contactors instantly on the car. The BMS also monitors the temperature of the battery. Your battery will not charge at all if it's below 0 degrees Celsius, which is about 32 degrees Fahrenheit. That's why sometimes when you go into a cold car in the garage, there's nothing there for regen. As soon as the temperature gets above 0 degrees Celsius, it'll start to regen and it'll start to take charge. Charging your Model S, you don't want to ever charge it all the time to 100%, because it's bad for the cells to sit around 4.2 volts, and that's what the car is at 100%. I would recommend leaving it in the daily range. But I do recommend balancing the battery every 2 months or so. Basically what you do with that, you plug it in, set the setting to 100% to charge it, and you let the battery charge to 100%. It'll take forever to charge that last 1% of it, and that's what it's doing at the time it's doing this. It's actually balancing all the cells. So it'll take the lower cells and bring them up a little bit, and it's gets everything in balance. But make sure once it's at 100%, don't let it sit there for a couple of days. Make sure to take it to a drive right away and get it down to 90% or below. Longevity of the packs are pretty incredible. In our fleet, we have a few cars that have over 100,000 miles on them, and there hasn't been any deterioration at all in the battery. They did a study. Yeah, go ahead. No, when it says zero miles on it, you're still at about 8% battery charge in there. It doesn't hurt you at all. Just be careful. Sometimes if your pack is really out of balance, it'll still say you have miles, but then it'll just stop going. I was using a customer's car, and I was cutting it close to a supercharger. It was still saying that it has 1% left. And then all of a sudden, next second I knew it was saying car powering down. I had to push it to the supercharger last 500 feet. So make sure you know your car well. But I was saying that in Europe they did a study with about 100 cars for the battery, and what they concluded that the batteries, if they're not abused, they're going to after 500,000 miles, they're still going to have 80% capacity left. So typically, could last a very long time. And then I'm going to have Ian take over. He brought one of the Tesla battery bricks. And essentially, the brick is full of those little cells. So you guys can pass that around. I'm going to get out of your way. Oh, actually, I'm going to give you the microphone.
So the BMS it doesn't actually keep track of all of the cells?
Oh, it does. Each brick, I'll have it does to a point, but I'll let Ian go into that a little bit.
Yeah, clip it on. All right. Can everyone hear me all right?
Typically, the optimum is to keep it around like 70. That's the optimum. That's fine. See, that's fine. 90's okay? 90's okay too.
Do you have the pointer? All right. Can everyone hear me all right? Yeah, no?
Who are you?
I'm Ian. I'm Pavel's little weekend helper. Come by and cause trouble. So I get to dig into things and learn too. So yeah, I'll talk a little bit about the brick. So there's 16 of these, as he talked about earlier. And how the kind of structure of the pack is you have 74 cells of those little guys that you're passing around in parallel at first, and that's when it's going to bump up amperage for your capacity. And then after that, they are paralleled together, series together into 6 series. So that bumps your 3.7 volts up to, let's see here, be 22.2 volts. And that's what your brick will be operating at. So, I mean, we can come up here later and you can kind of look at it closer. But these plates are what's going to be connecting, I guess 80 or 90 of them together or so. In order to bring that parallel part together. And then there's 7 plates in order to bring that up. In between the two, they'll switch. They'll flip-flop sides. And it's easier to see in person, and that does the series part. But in terms of what the BMS actually sees, it's going to see those sub-bricks. So there's 6 of them, 6 paralleled strings. No, that would be a lot of wiring and add a lot of weight and be pretty crazy. So instead it has little sense wires, and you can see there's a ribbon right here, and off there it's on each side, and that will have little taps, little bond wires that will go to each plate. And then so the resolution it has is each paralleled string is what it can monitor and check for balance that way. Additionally, that goes to here, so there's the BMB, battery managed brick. And that's what will kind of be the central unit to monitor all those voltages. And also it has 2 temperature probes on there to get 2 temperature readings of each brick as well. And that all ties to that center strut. See if that all ties into the center strut and go back to your BMS where it does that. Also it has 2 coolant loops, or one coolant loop. The 100 packs have 2. And that will flow through actually right here. You can see in these thicker parts, that's where your coolant is actually running through. So the coolant line does actually touch each individual cell. And you can kind of see that a little closer. You'll have an in and an out, and that goes through the whole brick up to, on that hump is where the coolant line will come in and out for that loop. But the bricks are pretty durable, pretty robust. It has, underneath these metal plates, there's a tough plastic, and they're more or less epoxied into that on each side, along with those side members. So I'm not aware of anyone that can really easily get at the individual cells without great deals of effort. But they are pretty durable. The one we have up here was actually damaged from the front drive unit impacting the top of the hump. And it did smush out a little bit and leaked out some electrolyte on about 7 of the individual cells. That's kind of a quick overview. Any questions or anything else I missed about the brick itself? Yep.
How much
Current? Yeah. The question is how much current. I don't know how many amps that would. Well, yeah, be 1,800 amps actually. Most it could do would be 1,800 amps. Yeah, at 22.2 volts for an individual one. Can I hold it up? That's more of a question of my strength. I mean, it's pretty heavy. They weigh about. Yeah. Yeah. If you want to check it out later, but they're pretty hefty, and they have plastic on the top and bottom. I guess another kind of unique thing is that has bond wires. So on each cell, there's one cell on one of these little dimples. And it's actually impressively small, but there's a little bond wire, and that actually works as the fuse as well. Because they're not internally fused, which was to save weight. Most 18650s you get commercially will have a little extra part on the top, and that's that's the little mini protection circuit on there. These do not have that. So if it arcs or something, it's going to blow. It's not just going to fizzle out or disconnect internally like a commercial grade 18650. So instead they have those little bond wires on there, and if things really go wrong, there's a term they call unzipping it, and that's where all those little bond wires will just all pop off and leave all the cells individually exposed or isolated. Yep. So I guess, yeah, some differences with the 100 pack. It has the 2 coolant loops through each brick to help cooling a little bit more efficiently. It has the double bond wires, and also I think it's 77 cells instead of 74 per sub brick. Total, this brick has about 444 for the 85s.
And that's that little battery that you're passing around. There's 444.
Yep, 444 in just this one. So, yep.
Bond wire blows.
Yep.
Will it still function?
It will still function. Yep.
Chances what's going to happen if one blows and the second one's going to blow because there'll be more stress, and it's just going to go unzip the entire brick, and then the car will be dead.
Yeah, depending.
If you're driving a car, it's just like one bond wire blow.
They could be. It would take a bit of time. It will slowly become imbalanced, but the BMS during I'll talk about that. I didn't talk about the bleed resistors. So it will balance that out over time, and just one isn't going to be a catastrophic change. It's not going to be huge. Yeah, so that would probably be okay. But yeah, it brings up a good point of the BMB on the bottom there. That's also controls the resistors, and that happens through those sense wires. So what it can do is if you have a sub brick that is kind of lagging, what it will do is it will use some resistors and bleed off some of that extra energy on the good ones to raise up the individual one. So again, the resolution of it isn't really per cell, but it's per sub brick, or 74 cells. So that's how balancing works. It just uses resistors, and that's why it takes a long time as well, because those resistors, if you look at them, they're not that robust. They don't have any cooling or anything, so it takes a while in order to bleed off that extra energy to work on those other ones. Technically, it is controlled by the computer, so Tesla could, if they wanted to, do a balance mid. Usually, oh yeah, sure. Sorry. The question was, why couldn't it just balance every time? So I mean, obviously, the way they have it structured is they top balance, which is going to be when you're at 100%, and that's kind of a more industry standard because everything's going to kind of draw down at an even rate. There is also bottom balancing. It's a big kind of feud between which one's better or not. However, when we popped in an 85 brick into a 90 pack, so that is inherently going to be kind of imbalanced. And it was actually pretty clever what they did. It did a top balance, but it accounted for that somehow so that it would end up drawing down to that minimum voltage at the same time, which is ultimately what's going to be that cutoff minimum. Yeah. When it's charging it, it's putting it at the right spot. Yep. So the reason why you want to go usually bottom or top balance in the end, though, is because that's when you have more information about where everything is relative to each other, where it's a little bit more obscure. The BMS is always constantly more or less guessing intelligently where your capacity is, because there's no real way to tell necessarily how much capacity is on a battery, because you could be at 4 volts, and that's more or less relatively going to always be 90% of a battery, but over time, how much it has will change, so that the amperage you get out of it will change, even though your voltages will still relatively be the same. So for that reason, that's why they want a top balance and bottom balance. Nominals, the question was what voltage are they at? Nominal they consider is 3.7 volts. Well, no, not 70. 70 is at about 3.92 for an 85 pack. Newer chemistries are a little bit different. They're more closer to like 65 or so. 3.2 is getting pretty low, yeah. I mean, even under load. 4. Yep. Any other? Yep.
So if the cells don't have the protective circuit,
Yep.
which protects against heat, for example, are there, it seems to me you would have a lot more destroyed cells.
Well, okay, the question was, since it doesn't have protection circuits to kind of protect them against that you'd have more destroyed cells. Tesla is very good about binning the cells, and that's really where they have a strong suit in doing that. So all the cells in here are going to be pretty similar. So with that way, things would have to go really wonky in order to actually have a problem of one getting out of line. And the temperature, I mean, the battery management, even in terms of heating or cooling through that coolant loop, I mean, it touches every cell. So they have pretty good control over it just with the thermal mass of the whole thing. And even just drawing it, I mean, you still have that 74 in parallel, so it gets evened out pretty well.
It's going to be pretty hard to overheat it. Like the hardest point on the battery is when you're supercharging, let's say it's don't get the most, because if you even a ludicrous car, if you're accelerating full blast, you can only do it for so many seconds, and that's usually not enough to bring the degrees 41 degrees.
And even once you do really start heating things up, it's going to start limiting your power on the car, and it will start protecting itself that way. So Tesla's battery management in terms of active cooling and heating is very impressive. That's what's really given them an edge. Question is, what's the C rating on the charge-discharge?
The question is, what is the C rating?
Yeah, I know. Yeah. Let's see here. I'd have to divide that out to see what it's actually doing during a supercharge.
C range is less than 1.5, because it's 85. Let's say
Yep.
it's 85 back, and you're putting 120 there.
Yeah. Well, that's by kilowatts, though, not by amperage. So it's slightly different. It would be about 1.5 or less, though. Yeah. Which is not really pushing it. Even while you're driving.
Could you explain the question and then explain the answer?
Oh, sure. So, question was about C rating, and that has to do with, I guess how would I describe it simply? It would be more or less the capacity of the cell used as a measure of discharge. So 1C would be in terms of amperage. So if you get 3,200 amps, milliamps out of it, sorry, that would be the capacity of one cell. 1C would be drawing 3,200 milliamps from it with a 3,200 milliamp hour cell. So it's kind of a measure of how much stress you're either charging it or discharging it. Is kind of an explanation of what C rating is. So generally 1C or even 1.5C, especially on discharge or charge, is not much compared to commercial grade 18650s. Different chemistries have different properties where they can be either better at that or longevity and so forth. So they can kind of specialize what cells they put in here. But just due to the voltages and amperages that they're doing on it, they're not really pushing individual cells hard at all, which is also part of how they can get away with that 500,000 miles with very low degradation, is because the average consumer, you're only using a certain part of that discharge every day. That helps it. It's not pushing it in terms of how much it's discharging it or charging it. That helps it. So all in all, they're pretty friendly with their batteries, and that helps to make them very robust. Yeah. Yeah, and if you go with some of those crazy lipos, you can go up to 3 or 4 or so. But yeah. Yep. All right. Sorry. Yeah. If you have any questions afterwards, feel free to bug us. Otherwise. Oh yeah. I mean, I said that briefly. He was wondering who I was. I don't know. I'm just an owner. I have about just under 90,000 electric miles between both our Teslas. And I bug Pavel on the weekends and so forth. But yep, sure. Yep. All right. Happy trolley.
So one of our last projects that we did was the. I'll say that at the end. I'm Pavel. I own PZ Global Auto. I'll have all my contact stuff at the end. I guess I probably should have put it in the beginning. It probably made more sense. But anyways, we rebuilt about 100 Teslas over the last couple of years. Primarily, we deal with the repairable Teslas that we fix, put them back on the road, and sell it to people with a discount. But we do kind of interesting projects sometimes. So one of the projects that we did was this 1968 West Coaster bus that I went and supercharged for a test, and it kind of went viral on that. I think it has over 300,000 hits or something like that. So I'll talk a little bit about how that whole thing works. So this bus originally was electrical. It had a top speed of 14 miles an hour. It had lead acid batteries, was a 48 volt system in there, and then it had 3 horsepower little electrical motors driving a GM differential in it, and that was enough to push that thing about 14 miles an hour, probably down the hill. Anyways, Hoppy Trolley wanted to get something a little bit more useful. They're going to be using this trolley for beer tours. They go from one brewery to another, so they told me they needed something to go at least 50 miles an hour and have at least 80-mile range in the cold. So then I figured Tesla has a pretty nice drive unit, a pretty nice pack, so let's make this a Tesla bus, I guess. So our first challenge was to fit a 1968 axle so it works with the drive unit. So what we had to do, we had to make a custom box in the Tesla drive unit, which I showed earlier in the pictures and my components. It sits inside of here, mounted solidly, and it's got CV shafts going into the axles here, and then the leaf springs would sit on here, and that would drive the original hub and the wheel. After we got all that together, great, everything fits, but Tesla has quite a bit of security in their code because they don't want trolley buses driving around and plugging into their superchargers. So we had to bypass some of that. So our choices were we could have moved the entire gateway of the car, so basically pretty much move every single wire from a Model S or a Model X into that bus and then splice each wire to make it longer, but that just seemed like a crazy amount of work because it's just lots of stuff. Just the stability control has all kinds of stuff in it. So we decided to build our own little controller here, and this was the first video of it working. Let's see if I can turn up the sound. I guess the sound doesn't come through the projector very well. Anyways, that little thing right here, that's the controller. And basically it's giving all the right signals to this drive unit. And if it had sound, you could see it spin right here. So then he's hitting the acceleration pedal, it's spinning. And he's going to put it in reverse here. And then he's going to hit the accelerator pedal, and then it's going to go in reverse. So that was the first part. Great, we got the motor working, but now how we're going to reliably get power to it? We still needed to do a lot of stuff because motor is relatively dumb compared to the battery pack and all the other stuff. So now we had to learn basically Tesla language. Over here, we're trying to, it's plugged in over here, and we're trying to figure out what exact messages in Tesla language the charger sends to the rest of the car to make it work. So you could see it's normal operation, but what is it going to start doing here? Something's going to start to do something funny. Okay, well, it stopped charging. Oh, look at this. I bet you your car doesn't do that. Little light show. Essentially, right now, what it's doing, it's learning what signals it passes. And once you figure out how this whole CAN bus works in the car, you can actually make it do lots of cool stuff. I can actually change colors in it. So instead of blinking green, you can make it blink red. But the main thing, we got the language, so we can further integrate it in the bus. Once we got out of the CAN and everything working, we powered the bus up but drove around on a Kia Soul pack just for our tests. We found out that the bus had a pretty short wheelbase and a full 85 pack didn't fit in there. That was the original plan. So we had to get a 70 pack and actually cut the front hump off of it. Change the bus bars, that's the things which all the power goes through. Put the fuse in separate and change all the cooling system inside of it. You can see this pack is pretty far tore down. Over here I'm pressure testing the cooling system because if one of the connectors where they go into the brick, if they got a leak in it, then you're in real trouble because basically you'll have antifreeze leaking inside your pack and eventually it'll corrode everything and you'll have a dead pack. But luckily everything's sealed up well, and so you could see it made it to the supercharger here and supercharged. A little bit about my company. We're located in Lino Lakes, and primarily, like I said earlier, we work with salvage Teslas, we sell cars. Now I've been getting into clean title ones as well. This is my email, and that's my phone number. And if anybody has any questions, I can go ahead in the blue shirt.
Was that a Raspberry Pi or any CAN bus you might have told that?
It's a little bit more complicated than that, but yeah, it's.
I'll talk to you.
Okay.
You want GMC and want to do that. I'm curious, how did you fake out the supercharger? That was through the night.
How the supercharger got freaked out? Yeah, well, when it plugged in, I mean, the whole system is not there. The drive unit is actually in dyno mode, so that gets us, we don't have to use it, kind of ignores all the ESP air codes that it has because the bus doesn't have any ESP on it. So it sits in the dyno mode, and then the rest of it is, pretty much, we're looking for all the signal that the car passes, and when the ID is plugged into the supercharger, it'll actually read the VIN number of the car, which originally it came a QuickBiz, but that doesn't really matter. We could change the VIN number to 0, or we can change it to 1 or anything, or we can have a floating VIN number, so every time it gets plugged in, it'll read something else. So, yes. Yes, they did. Hoppy Trolley got contacted by their. Oh yes, the question was, did Tesla contact me yet? And their Attorney General did contact me, and they asked us not to supercharge anymore because they're worried about custom vehicle using the chargers. But they were very positive about it. They thought it was a cool project. They just told me not to charge it there anymore. So.
Tell also how the Hoppy Trolley drives right now. How is it compared to the earlier 40 miles per hour?
Well, so the first time was this, the question was, how does the bus drive acceleration-wise? First, when we powered it with a Kia pack, the whole Kia pack was behind the wheel axles, and we had the power to set to 100%. And the first time we goosed on it, it did a wheelie. So we figured that was probably a little unsafe for a bunch of drunk people that would be in it. So we turned down the power to 30%. It still will have a top speed of about 110 miles an hour. And the acceleration, it's quick for a bus. I mean, it's not like Model X or Model S territory, but I was driving it, and there was a lane ending, and the Camry wanted to get in front of me, and I gave it a little power, and I could hear him downshifting, and his eyes were squared, but I pulled away from him. He couldn't do anything. Well, it's gonna, since the aerodynamic, the question was, what's the final range on the bus? With a 70 pack, I would estimate it to be about 140 miles. And that greatly depends on the speed you're going. If you're gonna drive that thing 70 miles an hour, it's gonna go through the battery pretty quick. But at 50 miles an hour, I'm guessing you can get 120, 150 miles, somewhere around that area. The climate system we're using in it is much better than Tesla. It's got a heat pump for air conditioning, and it goes one way, and then for heating and goes the other way. So it's pretty efficient. It only pulls about 5 amps versus Tesla's 20 amp. So
Where is it going to be operating?
it's in the question was where it's going to be operating. If you go online, Hoppy Trolley is the company that ordered the bus from us, and it's going to be operating here in the Twin Cities. I'm sure they'll have stuff on their website. It's still in the process of getting new upholstery in there and getting repainted. So
They're supposed to show up today.
it was pretty apart. I went by and looked at it today. It was sitting in a body shop, and like it had all the windows out and everything out of it. They were painting it.
The
So.
lady Martha, what's her name?
Michelle.
Michelle, yeah, she said she was going to show up.
Oh, okay.
Give information, but she never showed up.
Well, I'm sure you could track it on their website. Anybody else?
Thank you.
Excellent.
Okay. So it's around 7 for the discharge. Ian just calculated. Yeah, 1.3 for the charge, and then for the charge, it's for discharge, it's 7. Yep.
Okay, David, that was excellent.
Thanks. You're welcome.